In this section, in this video, we will be going over section 6.3. This section is about arc length and surface area. We are going to discuss various techniques to find the length of an arc and surface areas of a given surface. First, I want to go over this motivational example. Let's go over this example. Approximate the length of the curve f of x is equal to this particular function from x is equal to -2 to x is equal to 2 with 4 line segments. Then find a better approximation that uses 8 line segments. Okay. So first of all, notice that this is the upper half of the equation of a circle of radius 2 centered at origin. Okay, we have seen this one before many times. So if you graph this one on the interval -2 to 2, you will get a graph like this. Here is the graph you're going to get. On the interval -2 to 2, it will be a half circle like this. Okay. All right. So what does the question ask? We are asked to approximate the length of this arc, using 4 line segments. What I'm going to do is I'm going to divide this interval -2 to 2 into 4 subintervals because I am asked to approximate using 4 line segments. If it is 4 line segments, you divide your subinterval into 4. Your interval into 4 subintervals, and if you are asked to use 8 line segments to approximate, you are dividing your interval into 8 subintervals. But for the first part, I'm going to divide this into 4 subintervals. Clear? The 4 subintervals are going to be one from -1 to -2 to -1, -1 to 0, 0 to 1, and 1 to 2. Those are the 4 subintervals. Next, what I'm going to do is I'm going to compute the function height. I'm going to find the point corresponding to -1 on the graph. This is the point right here. And then for 0, this is the corresponding point on the graph. For 1, this is the corresponding point on the graph. And for 2, of course, this is the point. And -2, this is the point. Now I'm going to join these 2 points. These adjacent points will be joined. For these 2, I'm going to join it by a straight line like this. And then the next 2 points, again, I join it by a straight line. Next 2 points, you join it by a straight line. And last 2 points, you join it by a straight line. Okay. So if you join those points like that, now my claim is that the sum of lengths of these line segments, we have 4 line segments. If you take the sum of the lengths of those 4 line segments, that would be an approximation for the actual length of this arc. Would you agree with that? Geometrically, it's very clear, right? So this line segment is an approximation for this arc length. It's very clear. This arc length will be a little bit more than this the length of this line segment, but it's close, right? Likewise, every line segment is an approximation for the arc length in that region, in that interval. Okay. So as you can see, the sum of the lengths of these 4 line segments would be an approximation for the arc of this given arc on the interval -2, 2. So how do you find this length of these line segments? For example, how do you find this length? Well, that's not too bad because we know this point. This is -2, 0, right? This point is -2, 0. And then we can, of course, find this point by plugging -1 in your function. If you plug in -1 in this function, you will see that this point is going to be -1, square root of 3. -1, square root of 3. Similarly, this point, if you plug in 0 in your function, you will get 0, 2. This point is 0, 2. And then this point, if you plug in 1 in your function, you will get square root of 3. 1 comma square root of 3. This is of course 0 comma 2 comma 0. 2 comma 0. Now, as you can see, we can find the length of these line segments because we know the endpoints. We can find the length of this segment using these 2 points, using, of course, the distance formula. Remember, the distance formula is d is equal to square root of x2 minus x1 squared plus y2 minus y1 squared. I'll call this distance d1, d2, d3, d4. d1 is going to be square root of x2 minus x1 squared, that is minus 1 minus 2 squared plus y2 minus y1 squared, square root of 3 minus 0 squared. If you compute this, you will get 2. So d1 is 2. This is 2. Similarly, you can find d2, d3, and d4. And if you add them up together, you will get d1 plus d2 plus d3 plus d4 will be equal to 6.070. Okay. By the way, if you compute the actual arc length using the perimeter formula for a circle, this is a half circle, of course, you will see that this arc length is, actual arc length is, right, actual arc length is equal to 6.28319. As you can see, this is a nice approximation for the actual arc length, right? These two are very close. All right, that's the idea. Okay, that's how you approximate an arc length. You take a bunch of line segments and take the sum of lengths of those line segments to approximate the arc length. All right, let's move on. And by the way, if you use 8 line segments, that means you divide your original interval into 8 subintervals like this. In that case, you will see that your line segments are going to be like this. As you can see clearly from the geometry of this picture, this will be a better approximation than using 4 line segments, because this line segment, the length of this line segment is almost equal to the arc length in that region. The length of this line segment is almost equal to the arc length of the given graph on that interval. Okay, so on and so forth. You get a better approximation in each interval. As a result, you get a overall better approximation if you use more subintervals. All right, let's move on. Next, we have this definition 6.6, arc length of a function on an interval. Okay, here the idea is same again. Okay, suppose you are given a graph f of x on an interval, some graph. Okay, this is y is equal to f of x. This graph is given on the interval, say a to b. This is a, this is b. Okay, and what you do is, you remember your goal is to approximate the arc length of your function on the interval a comma b. That means you need to find an approximation for the arc length of this curve, which is in red. Okay, this highlighted curve. So how do you find the length of this curve on the interval a comma b? Well, again, the idea is same. We divide this interval into n subintervals, and we try to approximate the length of the arc length of this curve on that interval using the line segments, n line segments that you obtain using those intervals. Okay, so we divide this interval into n equal subintervals. Let's say this is the kth interval. This is your kth subinterval. This is xk minus 1. This is xk. Then I can find the corresponding function values. This value will be f of xk minus 1. And then the other value, this value will be f of xk. Okay, now I can find, I know this point. This is xk minus 1 comma f of xk minus 1. This point is xk comma f of xk. So if I know those 2 points, I can find this line segment. Line segment obtained by joining these 2 points. I can find the length of this line segment. What do? Use the Pythagorean theorem, right? Or the distance formula. Okay, in that case, I'm going to take, let me actually construct a small right angle triangle there. This is the first point, this is the second point. If I join these 2 points with a straight line, as you can see, I have a small right angle triangle here. This is my right angle triangle. This length is nothing but f of xk minus f of xk minus 1. Would you agree with me? This length. This is the difference in these 2 coordinates, right? That is f of xk minus f of xk minus 1. I'm going to take that as, I'm going to symbolize that as delta yk for a reason. Okay, so that's delta yk, and this is always delta xk. We know that the distance between xk and xk minus 1 is always delta x. That's the step size, right? That's always delta x. Delta x. Okay, now how do I find the length of this line segment? Using Pythagorean theorem, this square of this length should be equal to square of this one plus square of this one, right? So that means, let me write it over here. I'll denote the length of the line segment, this line segment in the kth interval by Lk. Lk is equal to clearly delta yk, pardon me, I'll write delta xk first, delta x, not xk, delta x, which is a constant, plus delta yk. Delta xk is x squared plus delta yk squared, and then you need to take the square root of that. By Pythagorean theorem, this line segment, I'll call this Lk. The length of this line segment is Lk. Lk is given by this expression, square root of delta x squared plus delta yk squared. Now I am going to modify this a little bit. I'm going to pull out the delta x squared. If you pull out a delta x squared, you get delta x times 1 plus delta yk squared divided by delta xk squared. That means delta yk divided by delta xk whole thing squared. Okay, remember you have delta x outside. So that means the length of this line segment in the kth interval is given by this expression. If I want, I can put this delta x here, okay? This quantity times delta x. Now, to approximate the arc length, this arc length on this interval, what you need to do is, you need to sum up all these lengths of, you need to take the summation of lengths of all these line segments, right? You need to take the summation of line segments, length of the line segment in each interval. So you take the summation of this one. K goes from 1 to n. That will give you the sum of n line segments. That will be an approximation for the arc length of this function on that interval a comma b. Okay, that is nothing but this expression. As you can see, this thing is same as this thing. Okay, so you take the summation. K goes from 1 to n because you need to accumulate all those line segments, right? You need to sum up the lengths of those line segments. So you take the summation. And now, if you take the limit as n goes to infinity, that means you are making your delta x smaller and smaller. What happens when you do that? You get the exact arc length of this curve when you take this limit. Okay, that's the idea. Here again, this delta x, delta yk is f of xk minus f of xk minus 1. Okay, and delta x is always defined by this quantity b minus a o n. All right, so we have this definition. So the arc length of f of x from x is equal to a to x is equal to b is given by this formula. Limit as n goes to infinity, the summation of this expression. All right, let's move on. Okay, next, I want to go over this example. Approximate the length of one period of the function f of x is equal to sin x by using the formula and the notation in definition 6.6 with n is equal to 4. Okay, for each k, describe xk, yk, and delta yk. Okay, let's try to do this problem. We are asked to use one period and n is equal to 4. First of all, notice that the graph of f of x is equal to sin x is drawn in a period, in the period 0, 2 pi here. Okay, this is the graph of sin x on the interval 0, 2 pi. Notice that 2 pi is a period. Okay, so we need to approximate this length of this graph or length of this arc on that interval. Okay, using 4 subintervals because n is equal to 4. So what I'm going to do is I'm going to divide this interval into 4 subintervals. This is clearly pi over 2. This is going to be pi. This is going to be 3 pi over 2. Now I can take line segments. Okay, I can consider line segments. On this interval, I take my line segment to be this line segment. I join those 2 points. I join these 2 points to get the line segment in that interval. To get the line segment in the other interval, second interval, I join these 2 points. And then to get the line segment in the next interval, I join these 2 points. Then to get the line segment in the last interval, I join these 2 points with a straight line. Okay, now we need to identify these quantities, xk, yk, delta yk. Okay, remember by definition, xk is given by a plus k times delta x. Delta x is clear here. Delta x is b minus a over 2, b minus a over n. That is 2 pi minus 0 over n. N is 4. That is pi over 2. Okay, and a is also clear. A is equal to 0, b is equal to 2 pi. That's the right endpoint. B is the right endpoint, a is the left endpoint. Okay, now I can find all the x values. x0 is equal to a is 0. And then x1 is equal to a plus k delta x, which is 0 plus k delta x. K times delta x is pi over 2. K is 1. Okay, 1 times pi over 2, which is pi over 2. And then x2 is equal to similarly pi. x3 is equal to 3 pi over 2. x4 is equal to 2 pi. So we identified all the xk values. Okay, and then yk values. How do we identify yk? Remember, yk is f of xk. Okay, yk is f of xk. That means y1 is equal to f of x1. Of course, first of all, you can find y of 0. Let me find y of 0, f of x of 0, that is 0. And then y1 is equal to f of x1. That is, remember, your x1 is pi over 2. If you plug in pi over 2 in your function, you get 1. y1 is equal to 1. So on and so forth, you will get y2 is equal to 0. y3 is equal to -1. y4 is equal to 0. And then what about delta yk? Can you compute delta yk? Well, we know by definition delta yk is equal to f of xk minus f of xk minus 1. That's the formula for delta yk. Okay. Now we can find all those values. Delta y0 is equal to f of, pardon me, delta y1. Delta y1, k starts at 1, right? Because this is delta y, this is delta y1. This difference, k starts from 1, okay, not from 0. Delta y1 is equal to f of x1 minus f of x0. And of course, you can calculate this. You will get it is 1. Similarly, delta y2 is going to be f of x2 minus f of x1, which is minus 1. Similarly, delta y3 is going to be minus 1. Delta y4 is going to be plus 1. Okay, so we identified all the quantities, and then we need to approximate the arc length. How do you approximate the arc length? We approximate the arc length by the lengths of these 4 line segments. You have 4 line segments. You know how to find the length of this line segment, right? Of course, you can find the lengths of these 4 line segments using this formula without the limit. Okay, k goes from 1 to n, 1 square root of 1 plus delta yk divided by x delta x squared times delta x. Okay, you can use that formula to find it. Right, here is the formula to find the lengths of the 4 line segments, because I have k goes from 1 to 4 here because I have only 4 line segments here. So we need to find the sum of lengths of those 4 line segments. If you plug in k is equal to 1 in this expression, you get 1 times, of course you need to have a square root, plus delta y1 divided by delta x squared times delta x. Of course, you know all these quantities. 1 plus delta y1. Delta y1, you found it. Delta y1 is 1. Okay, so you can put 1 here. Delta x is, of course, pi over 2. Okay, you also found that. You can plug in that here, plug in that here, plug in delta x here, and then you can compute this value. If you compute this value, you will get 1.8621. Similarly, if you compute 1 plus delta y2 divided by delta x, whole thing is squared, of course, the square root of that delta x, you will get 1.8621 again. And you will see that the other ones also, you will get the same value. Let me write it here. Here, this is y3, y4. Delta y3, delta y4. This will be 1.8621, 1.8621. And you will be wondering why you get this same value everywhere. That's clear from the graph. If you take the sine graph by symmetry, these lengths are equal. This length is equal to this length. And of course, that is equal to this length. That is equal to this. Okay, that's why you get the same value. Now, the approximation will be the sum of these 4 values. That is equal to 1.8621 times 4. You have 4 of them. Okay, that is 7.4484. All right, that completes that example. Let's move on. Next, we have a formula to calculate the arc length. Okay, so let's go over this theorem, theorem 6.7, arc length as a definite integral. Suppose f of x is a differentiable function with a continuous derivative on the interval a comma b, then the arc length of f of x from x is equal to a to x is equal to b can be represented by the definite integral given by this. Okay, so arc length of f of x from x is equal to a to x is equal to b is given by this definite integral. Okay, definite integral from a to b is square root of 1 plus f prime of x squared dx. Okay, so this formula can be justified using similar ideas that we used in this definition, but I'm not going to go to the explanation here. Now we are going to see some applications of this theorem. Okay, so we are going to find the arc length using this particular formula. By the way, the proof of this theorem is in the book. I will let you read that. It's a so straightforward proof. All right, next let's go over this example. Construct and solve definite integral to find the exact length of the curve traced out by f of x is equal to x to the power 3 over 2 on the interval 0, 3. Okay, so we can, this is a straightforward application of this theorem. Okay, if you graph this function on this interval, you will see a graph like this, and we are asked to find this length, this arc length on the interval 0, 3. So this is a straightforward application of the previous theorem. We can use this formula to calculate that length. Okay, notice that your a is 0 in this case, the lower limit. The b is 3, the upper limit, and of course you can find your f prime of x. So the arc length will be equal to integration from 0 to 3, pardon me, 1 plus, first of all, I need to find the derivative of my function, right? Let me find the derivative first because I have to plug in the derivative. F prime of x is 9 over 4 pardon me, f prime of x is 3 over 2 times x to the power 1/2. And then remember, in the formula, you need to put f prime of x squared, right? So I calculate f prime of x squared there itself. So that is 9 over 4x. So now I can go with this formula now. So this is going to be equal to square root of 1 plus f prime of x squared, that is 9 over 4x, too long, dx. Okay, now it's all about calculating this integral. Of course, you can use the substitution. U is equal to 1 plus 9 over 4x to calculate this integral. Okay, if you use this substitution, you should be able to calculate this integral, and you will get, I'm not going to show the calculation here, 6.096. Okay, all right, that completes that example. Let's move on. Okay, next example I want to work on is this one. Construct and solve definite integral to find the circumference of a circle of radius 2. So we need to find the circumference of a radius of circle 2. Circumference of a circle of radius 2, pardon me. So radius is 2. How do you find this circumference? Circumference means this length. This length. Okay. Well, again, I'm going to use a similar technique that we used in the previous example. We know that the upper half circle, equation of the upper half circle of a radius 2, which is centered at origin, is given by x squared minus 4, right? Square root of y is equal to x square root of x squared minus 4. That is the equation of the upper half of the circle. Circle of radius 2, of course. Okay, this equation is y is equal to square root of x squared minus 4. We know that. What I'm going to do is I'm going to find this arc length and double it to get the circumference of a circle. Okay, So let's find this arc length and let's double it. Okay, how do we find that arc length? That is not bad because we have a formula now to find the arc length of a given function on a given interval. Okay, here the interval is here this should be -2. Okay, here the interval is -2 to 2. I know the function. I can find the arc length using the formula that we discussed. Here is the formula. Arc length is given by this formula. For that, I know my f of x. I can calculate f prime of x. This is my f of x, okay? Your f prime of x your f prime of x is going to be this expression. You know how to differentiate this one. Now I'm going to square this one because in the formula I need f prime of x squared, right? So I will calculate that here itself. That's x squared over 4 minus x squared. Now I'm ready to go with my formula. Okay. Arc length. I'll call this S. Okay, this length is S. The arc length is S. S is equal to integration -2 to 2 square root of 1 plus f prime of x squared, that is x squared divided by 4 minus x squared dx. Okay, that's the integration you have. All right, now to calculate this integral, I will leave that as an exercise for you. If you calculate this integral, you should get 2 pi. That means the circumference of the circle would be 2 times this length, that is 2 times 2 pi, which is 4 pi. And this well coincides with the formula. You know that how to find the circumference of a circle, that is 2 pi r. R in this case is 2. If you plug in 2 here, you get 4 pi, right? That's what you get here. Okay. All right, that completes that example. Let's move on. All right, next I want to go over this theorem, theorem 6.8, the surface area of a frustum. Frustum is an object of this form, okay? It's kind of you take a cone and then you remove the top part of the cone. If you remove this piece, you get a frustum, okay? You take this radius of this surface to be P and the radius of the bigger surface to be Q, okay? And this is called the slant length. It is denoted by S. All right, so now how do you find the surface area of this frustum? Surface area means area of this surface. Okay, here is the theorem. Here is what the theorem tells us about the surface area. A frustum with radii P and Q. This is P, this is Q, okay? And slant length S, as shown in the figure, has the surface area S is equal to 2 pi rs. That's the surface area. Surface area is 2 pi rs, where this r is the average of this bigger and smaller radii. Okay, you take the average of these two radii, P plus Q over 2. That's your r. Okay, and of course this S is this slant length. All right, I'm not going to prove this formula. Let's move on and see some applications of this theorem. Let's go over this particular example. Use 4 frustums to approximate the surface area of the sphere of radius 2 centered at the origin. This sphere can be realized by rotating the curve f of x is equal to square root of 4 minus x squared from x is equal to -2 to x is equal to 2 around x-axis. We have seen that many times, right? So you take this curve, this half circle, which is y is equal to square root of 4 minus x squared, and then you rotate this region about x-axis. Then you get a sphere, right? You get a sphere. This is a 3D object, okay? Even though it looks two-dimensional, it's a 3D object. This is your sphere. We are asked to approximate the area of this sphere using 4 frustums. If you are asked to use 4 frustums, what you do is you divide your interval -2 to 2 into 4 subintervals. Okay, this is the first subinterval. This would be -1, and then -1 to 0, the second subinterval, and then 0 to 1, third subinterval, and then 1 to 2, fourth subinterval. Now, in each subinterval, I'm going to construct a frustum. In this subinterval, here is the way I'm going to construct the frustum. I take a cross section here, and then I join these points. Basically, what I do is I join these 2 points, and then I get a region here, right? I rotate that region about the x-axis. Then you get a solid like this, right? I'm going to approximate the area of your sphere in that region by the area of this solid. That's my idea, okay? And then the next frustum is going to be, I'm joining these 2 points now, the straight line. And then I get a region, right? This region. I rotate that region about x-axis. Then again, you get a solid, right? Again, you get a solid. This time, this is the solid that you're going to get. It's a 3-dimensional thing, okay? When you rotate that above piece, you get a solid like this. This is a frustum. I'm going to approximate the surface area of your sphere in that interval, in this particular interval, by the surface area of this frustum. That's a good approximation, right? You can see that from the geometry of this figure. Likewise, I'm going to have 4 frustums. This is my second frustum. And here I have my third frustum. My third frustum. And here is my fourth frustum. Okay, now I'm going to find the areas of each of those frustum, and I'm going to add those areas to get an approximate for the area for your circle. Okay, let's go with the first frustum. How do I find the area of the first frustum? First of all, I have a formula for that, right? From the previous theorem, we have this formula. Okay, I will call the first frustum S1, the area of the first frustum S1, the area of the second one S2, and then S3, S4. Let's focus on S1 first. Okay, how do you find S1? Well, for that, I can use this formula. First of all, I need to figure out my R and S, right? How do I figure out my R? R is, remember, P plus Q over 2, right? For the first frustum, what is P, what is Q? P is 0, right? For the first frustum, here, this is clearly a cone. So that means there is no P. P is 0. The Q is this height. So that will be, this will be 0 plus f of -1 over 2. Okay, that's the value of R. And then what is the value of S? How do I find the value of S? Value of S is the slant length. Slant length is, you can find this slant length by finding the distance between these 2 points. This point is -2, 0. This point is -1, f of -1. Okay, so let me write it here. This is -2, f of -2. Of course, you know that f of -2 is 0, but let me just write that. This is f of -1, f of -1. So I can find that length. So that is square root of -1 minus -2 squared plus f of -1 minus f of -2 whole thing squared. Okay, if you compute this, you will get 2. Okay, you can of course compute these things by plugging these numbers in your function. If you compute this, you will get your slant length is 2. Now I can find S1 using my formula. S1 is equal to 2 pi rs. I know my r, 2 pi. My r is this one, 0 plus f of -1 divided by 2, which is square root of 3 over 2. Square root of 3 over 2 times s. S is the slant length, which is 2. That will give me my S1. S1 is going to be S1 is equal to 2 pi times the square root of 2, because 2 cancel, you get this one. Similarly, we can find S2, S3, and S4. Okay, you follow the same procedure. You identify your radius by using this formula, P plus Q over 2, and then you find the slant length by finding the, for example, if you go to the second frustum, you can find this slant length by finding the distance between these 2 points. Those 2 points are known, so you can find the slant length. And then, of course, you can find your R by taking the average of this radius and this radius. Okay. All right. If you find S2, S3, and S4 and add them together, if you add all of the 4 together, you will get S1 plus, S2 plus, S3 plus, S4 is equal to 46.04. Okay, of course, you need to calculate this. Okay, I'm not going to go into detail because it's the same thing, same procedure as you used over here. All right, that completes that example. Let's move on. Next, I want to go over this definition 6.9. Suppose f of x is a positive differentiable function with a continuous derivative. The surface area of the solid of revolution obtained by revolving f of x around x-axis from x is equal to a to x is equal to b is given by this formula. Okay, this is equal to limit as n goes to infinity, the summation of this thing. And here, this delta yk, as before, it is f of xk minus f of xk minus 1. And of course, these are defined the same way that we have been defining them in the past. Okay. All right, what does this tell you? This tells you a way to find the surface area, okay, of a surface obtained by revolving a curve about x-axis. Right? Here is the picture. Let's look at the geometry. Suppose you have a graph f of x like this on the interval a comma b. What you do is you rotate this curve about x-axis. If you rotate that, you get a surface, right? If you rotate this about x-axis, you get a surface. We are interested in the area of that surface. Roughly, you will get a surface like this. You need to find the area of the surface that you obtain by rotating this curve about x-axis. Okay, so we need to find the area of this surface. So how do you find the area? Again, the idea is you divide this interval a comma b into sub-intervals, and let's say your kth sub-interval is this one, xk minus 1, xk. And then I'm going to construct a frustum in that sub-interval. In that sub-interval, I'm going to construct a frustum. This is my frustum. Here the graph should be a little bit downward, clearly. Okay, here is my frustum. This is a 3D object. Okay, basically you rotate this region about x-axis, then you get a frustum. What I'm going to do is I'm going to approximate the surface area of my object by the surface area of this frustum in that interval. If you find the surface area of your frustum in this interval, you will see that that's going to be this big quantity. Okay, I will leave it up to you to justify that. The area of the frustum in the kth interval is going to be this much. Okay, now what you do is you have n of them, right? You have n frustums, so you take the summation. Okay, goes from 1 to n, and then at the end of the day you take the limit as n goes to infinity to find the exact area. Okay, when you take n to be bigger and bigger, you get more accurate answers, right? So that's the idea. So carefully look at it. This is actually the average radius of the frustum, that is p plus q over 2. That can clearly be seen here. And this is nothing but the width of the, this is the slant length of the frustum. If you compute this slant length, you will see that that's going to be this quantity. All right, let's move on. Now we have this theorem. This theorem gives you a formula to find the exact area. Okay, exact area of a surface obtained by rotating an arc around x-axis. Let's go over this theorem. Actually, this, first of all, let me go over this theorem. Suppose f of x is a positive differentiable function with a continuous derivative. The surface area of the solid of revolution obtained by revolving f of x around x-axis from x is equal to a to x is equal to b is given by this definite integral. Okay, that means this gives you a way to find this exact surface area of this surface. Okay, basically this formula is deduced by this infinite summation. This summation becomes a definite integral as long as you take the limit as n goes to infinity. In our context, it's going to be a definite integral, right? We can show that this infinite summation is the definite integral given here. Okay, so we have a formula to find the exact surface area of a surface obtained by revolving f of x around x-axis on the interval a to b. Okay, let's now look at some example. I want to go over this example, our last example. Construct and solve definite integral to find exact surface area of the surface of revolution obtained by revolving the graph of f of x is equal to x cube around x-axis on the interval 0, 1. Okay, basically here is the graph. Okay, here is the graph of x cube on that interval 0, 1. Okay, you rotate this curve about x-axis, then you get a surface, right? Then you get a surface like this. You need to find the area of that surface. Of course, you can use the previous theorem to calculate that surface area. Let me copy that to the other side, the formula. Here is the formula. In the formula, notice that we need f prime of x squared, right? Here we need f prime of x squared. So let me calculate that. F of x is given. F prime of x is 3x squared. So f prime of x squared will be 9x to the power 4. Okay. Now I can go with the formula to find the exact surface area. Exact surface area is equal to integration. Oh, I should have 2 pi in front. 2 pi times integration. What is my interval of integration? This is 1. 0 to 1. Okay, so integration from 0 to 1. F of x times, f of x is x cubed, times the square root of 1 plus f prime of x squared. That is 9x to the power 4 dx. Okay. Now using a small substitution, you can solve this integral. Use the substitution. U is equal to 1 plus 9x squared, 9x to the power 4. Okay, this will reduce this integration to an easier integration that you can compute, and that will give you the answer to be, you should get, if you do the calculations correctly, 5 over 18 times 2 over 3 times the square root of 1000 minus 2 over 3. Okay, that should be your final answer. All right, that's the last example that I wanted to go over. With that, we conclude section 6.3. I'll stop there and I'll see you next time.